Thank you very much for kind introduction, and it's my very great pleasure to join this exciting event. And I just met previously, if you heard our discussion, our chatting, yeah, I wanted to come to visit everyone and to attend the physical meeting. However, facing to the global pandemic, we have to postpone the meeting to some moment in the future. But still, it is really great to see such a online precursor to introduce various advanced topics about the physics of the very early universe. And today, I'm going to talk about a field that I have been working on for many years, and I also see many of my long-term collaborators, including my previous supervisors, in this meeting. So the topic is about the non-singular bounce cosmology and the relevant the development of the perturbation theory from the perspective of effective field theory approach. I just want to mention, in the past 2 days, I noticed that we had Patrick Peter to also talk about the bounce cosmology, and also Jerome Quintin talking about the limiting curvature bounce non-singular cosmology. So I guess most of the participants, especially for the young scholars, probably have already had a quite clear picture what is bouncing cosmology. But before that, I want to begin with a case that I want to carry out the picture of effective field theory. That is the effective field theory description of inflation. So a very typical lesson that we often learned from about the inflationary cosmology is that we can apply Lagrangian over free massive scalar field and just embed it into a especially FRW cosmological background. Then one can write down the Friedmann equations just like this slide showed, and then following the evolution, especially if you set up a particular initial condition that a scalar field begins evolution with a very small velocity at a very high energy scale, then this model is able to yield accelerating phase at a high energy scale. And because it's slow dynamics that makes the potential energy become dominant, so then this the dynamics of the scalar field behaves just look like a cosmological constant, so that we can get this inflationary phase at a higher scale. But of course, this is a very first lesson that we can learn about the early universe physics from the perspective of effective field theory. And of course, from the beginning, I want to warn you that regarding the effective field theory, we always have the limit on understanding the physics beyond, for example, at a higher energy scale. For example, for inflationary cosmology, the amplitude of the scalar field is typically larger than Planck mass. This is often brings some kind of a conceptual issue when you consider the higher order quantum corrections. And also, even with this scenario, we could get some first, the initiative achievements addressing the traditional thermal Big Bang cosmology. For example, inflationary cosmology can help us to understand the horizon problem, the lattice problem, and the monopole problem, which I guess almost all of you get clear very much. And also based on the inflationary cosmology, a very successful perturbation theory has been developed, and the primordial fluctuations seeded from the quantum fluctuations of the scalar field can eventually lead to the formation of the larger scale structure, and also can explain what we observed in the cosmic microwave background anisotropies. From the observation, it tells this is a nearly scale invariant path spectrum of primordial density perturbation, and that has been in agreement with the prediction made by the power law parameterization of the inflation cosmology. And also, according to the perturbation theory developed based on this background evolution, we can get to know inflation typically predicts a small amount of the primordial non-causality, which means there might be some non-linear perturbations, but typically this part of the contribution is suppressed by the slower parameters. And also, it typically predicts sizable primordial gravitational waves, and that drives the experimenters, especially the cosmological experimenters, to try to look for the primordial gravitational wave in the future CMB observations. And as I mentioned, because this is effective field theory, so we know there are some defects. For example, there's a famous Transplanckian problem, like the perturbation mode with the physical wavelengths to be shorter than the Planck scale. And also, inflation has inherited the issue coming from the thermal Big Bang theory, that is the initial Big Bang space-time singularity issue. And try to addressing these conceptual issues, then that's the motivation why people often think about the alternative scenarios to the over the very early universe, that is the bouncing cosmology. So this is the outline that I want to carry out with all of you. So I will very briefly review the various bounce cosmologies, and then talk about the effective model building of the bounce cosmology, and point out some challenges and some points or some issues that we have to be aware of. Then, based on the bounce cosmology, we, especially for some particular contracting dynamics, which is referred as the meta bounce, then there is a very well established perturbation theory. But then, along the theoretical development and the observational development, we found there are various constraints on bounce models. And then I will give a very quick summary by stating my understanding in this field. So back to probably, about 20 years ago, so there was a very famous model, that is Ekpyrotic model. So that model was proposed based on at that moment, the string cosmology. So it describes the if we have two M-branes in a high dimension, say for example the 5 dimension, and then if we have these two M-branes to be attractive with each other by some the long open springs, then this can yield periodically collision between these two branes, and that can give rise to the non-singular cyclic universe at a higher dimensional space-time. But if we can reduce this scenario back to the 4th dimension, then one can write down the effective Lagrangian. This Lagrange, the action. This action is consists of the standard Einstein gravity, the Hilbert-Einstein action, and plus a scalar field. And by tracking the rolling of the scalar field along the potential, then one can get in each cycle this universe could have experienced the, for example, dark-ended domination, the deceleration and turnaround to the contraction, and this contraction is referred as the Ekpyrotic contraction, which I will talk about later. And then it will reach the big crunch and bounce in, and then to begin the expansion. But this bounce in 4-dimensional is a singular bounce. So usually it would arise some conceptual issue about how the perturbation can transfer through this singularity in 4 dimensions. And in the literature, there are many proposals of the non-singular cosmologies. So here I just named a few. It's totally not the full list, but I would like to mention, for example, the pre-Big Bang cosmology is based on the non-perturbative effects, and the string gas cosmology is based on also the non-perturbative thermal non-local system that was up to many years ago. And recently there is a quite well developed scenario. It's called the meta bounce cosmology, and also the meta bounce cosmology refers to when the universe was contracting, it look like a mass domination, and of course from some quantum gravity, like a two-loop quantum cosmology, use the quantum structure of the space-time to avoid the singularity. And also there's the music cosmology and some non-conventional field theory like the Lewick theory to drive the Lewick bounce, or the new Ekpyrotic cosmology, Galilean genesis. Actually, I believe Yamaguchi-san will talk about that later. And then previously, I remember Jerome Quintin talked about the bounce cosmology derived from the limiting curvature hypothesis. And also Patrick Peter talked about getting the bounce cosmology using the special curvature. So, well, facing to so many models, so where should we begin? Okay, I would like to begin with some kind of the challenges. This is my personality. I like to find something wrong and then try to understand how to overcome it. So let us take a look at the challenges of constructing a non-singular bounce from the background level. So regarding the background level, if you want to get to know the cosmological evolution, there's a very crucial parameter, that is the background equation state parameter. From the thermodynamics, we know the equation state parameter usually is defined as the ratio between the pressure and the energy density. However, if you let us assume the Einstein gravity is not modified and we can write down the Friedmann equation, then we can actually effectively identify this W to be expressed in terms of the Hubble parameter and its time derivative, that is W equal to -1 minus 2 times h dot over 3h squared. And in order to get a bounce, of course, universe should start with a contraction, right? So at that moment, h is less than 0, it's negative. And of course, usually the W is larger than -1 because this is required by the non-energy condition. And by transiting to the regular thermal expanding history as observed by our observations with h larger than 0 and W also larger than -1, then this means the non-singular bounce has to take place when at some moment when h equal to 0 and h dot is larger than 0. So keeping this condition in mind, then we can write down the Friedmann equation as the following. So this is in the middle of this slide. You can see the h squared is determined by the constant, effective special curvature, the matter the regular matter components, the radiation components, and you can also include the anisotropy back reaction. And you can generally argue there's a scalar field phi contribute the effective energy density, and this phi comes from the effective field theory approach. And so there are two issues that need to be aware of. One is we need to dilute the unwanted anisotropy. This is the contribution coming from the sigma square over a to 6. That because when the universe is contracting, this term would very easily become dominant over. So that means there should be some Ekpyrotic matter is required. So, and that means for this scalar field, we wish there at least there should be in sufficient long period the equational state parameter of this scalar field to be larger than 1. This point was pointed out by Corey, Overy, Steinhardt, and Turl back to 20 years ago. And for non-singular bounce, as I mentioned, the condition requires h equal to 0 and h dot larger than 0. So that means there should be a duration of the violation of the non-energy condition around the bounce, because W has to evolve from above -1 to below -1. And one example, not quite successful, but at least there is a phenomenologically clear scenario, is a so-called quantum bounce, because there is the crossing over behavior, which often referred as the quantum scenario. And then the violation of non-energy condition often lead to the quantum instability. For example, I mean, just to give one example, let's say we have a scalar field. Its Lagrangian is write down as the kinetic term combined with the potential term, and the simplest way to violate the NEC is to let the kinetic term to be negative in front of the sign. So that is a ghost field. But of course, we can make it as the function of x. So at a high energy scale, we can argue this ghost field can be condensated at some regime. So this is referred as a ghost condensate scenario. And with this kind of scenario, the NEC can be spontaneously broken at some relatively infrared regime, and that can yield a non-singular bounce. So this work was referred as the so-called new Ekpyrotic cosmology, as proposed by these two references. But later on, people realized for this kind of scenario, even it is a so-called new Ekpyrotic model, using the Ekpyrotic phase, one can dilute the anisotropy in the contracting phase. However, this scenario actually cannot really address the anisotropy problem, because if you have the initial moment at some point, for example, Ekpyrotic beginning moment, then when along with the contraction, there is a period of the Ekpyrotic phase, but then it just should evolve back to the ghost condensate phase. So with this phase, no matter how much the anisotropy can be diluted in the Ekpyrotic contraction, after that, and when the universe evolves to the ghost condensate phase, the anisotropy would grow back, and so does the curvature term will grow back. So that was pointed out by Xue and Steinhardt about 10 years ago regarding this scenario. The challenge still remains there. And also motivated by the dark energy study, I mean, this is a part of the perturbation theory of the dark energy. It states there is a so-called no-go theorem to forbid the equational state of the scalar field to cross over W equal to -1, because there is a severe gradient instability. Actually, this issue eventually inspired a lot of studies in the literature, no matter the dark energy physics and the early universe physics. So now, in the following, we would like to try to understand how we can make the effective model building towards the non-singular bound. Especially as a first step, we want to see if this realization can be achieved by a single scalar field. And as I mentioned, because there was used to be the theoretical no-go theorem for forbid the equational state of the single scalar field to cross over -1, that is the gradient instability approved. But then there are always some kind of very smart guys, right? Like since 2000, I think it's from the end of 2008, then there were a couple of people raising this interesting question. That is, if we can generalize a single scalar Lagrangian by involving higher derivative terms, can we get this? Can we make sure the degree of freedom remain the unique? To be one scalar degree of freedom without involving any ghost instability. So this eventually comes to the so-called Galilean model, or today we call it as a Hondesky model, because eventually we find back to 1974, the Hondesky has already proposed this Lagrangian, and then we make use of this Lagrangian and try to raise another question. Using this single scalar field, can we get the non-singular bounce? So inspired by the previous studies, like the new Ekpyrotic cosmology and the perturbation theory developed from the Hondesky Lagrangian, we try to combine these two, the advantages of these two different theoretical scenarios. One is to use to keep the ghost condensate so that we can drive a short duration of the non condition spontaneously. But then we did a slight deformation by changing by replacing the standard kinetic term x in front of the coefficient in front of this term. We write it down as 1 minus g as a function of phi. So when scalar field phi evolves, these coefficients will be changed. So we have some kind of the chance to to break the constraints that previously I mentioned. If you use the Ekpyrotic phase to dilute anisotropy, but if the scalar field can evolve to some other value, then it can change the duration of the ghost condensate to be a different way. So then we can avoid the growing back period. And also, the reason why we keep the Hondersky operator, that is because we wish to remove the gradient instability throughout the whole evolution. So this and then this is the model that we have been taken here. Then we can apply this model to into the FRW background, and then we can derive the end density and the pressure, and then also the general Klein-Gordon equation. With all these setups, then you can calculate the background evolution. Of course, this is a very complicated model, so then we have to make appropriate simplification so that the calculation can be trackable. So what we did is to separate the background evolution into basically the Ekpyrotic contraction and the immediately evolving connected with the ghost condensate phase, and after that, during the ghost condensate phase, the universe could experience the bounce very smoothly, and after that, it will evolve to the short period of faster rho expansion. So I'm not going to the details of this slide, but we can discuss later if you have interest to discuss the detailed issue. But here I would like to directly show the numerical evolution. So here is the numerical plots of the Hubble parameter equation of state evolution and the evolution of the scalar field itself. So from the first plot, the left panel, you can see this is a non-singular bounce because H evolves from the negative value to positive value very smoothly. And from in the middle of the plot, it shows the evolution of the equation of state parameter W. And W in the contracting phase is larger than 1, so that guaranteed the Ekpyrotic phase is over there. That can be used to dilute the anisotropy. And after the bounce, W approaching to unity, approaching to 1, so that corresponds to the so-called faster rho phase. And around the bounce, you can see. Around the bounce, you can see W evolves from above -1 to below -1. That is a violation of the nine condition.
I'm sorry, there is some disturbance in the background. Shantraj, can you mute all others, please? Shantraj? I'm sorry, I hope it is settled now. Please continue.
No, it's okay. It's okay. Yeah, I know. This is totally no problem. Right. So yeah, anyway, this is a very good example to illustrate indeed a smooth non-singular bounce indeed can be achieved by a single scalar field. And later on, we also include the effect of anisotropy by considering this Bianchi metric. And then again, we examined the evolution of a Hubble parameter and the evolution of the effect of end density along different directions. So basically, we want to verify this model is robust against the anisotropy instability. This was a work that actually many years ago I've done with Robert Brandenberger and Patil. And here are a few comments by what we can learn from this part of a study. That is, non-singular bounce indeed can be realized by a single scalar field under the help of both the ghost condensate and the Hondersky operators, and also the primordial anisotropy diluted in the Ekpyrotic contraction would not grow back due to this the deformed ghost condensate Lagrangian, and thus this model is free from the PKL instability. But then the question is, we should check again if this is indeed stable against all of the ghost instability and the gradient instability. And what about the primordial power spectrum? If it can provide some alternative scenarios to, different from inflation that can also satisfy the cosmological observations. So then we go to the perturbation theory. Well, I guess many people have seen this the comparison of these two plots. Well, the left side is a very famous diagram plot by Robert Brandenberger, back to his famous paper in 1999, and it shows why inflation is successful in deriving a scale invariant spectrum, and how it's the causal mechanism to describe the evolution of the perturbation. So that is during the inflation, the fluctuation originally comes from the sub-Hubble scale, and that can be regarded as the quantum mechanical origin. And then during the inflation, of course, the Hubble radius remain constant because h is almost constant, but the physical wavelength of the fluctuation can be stretched to very, very long, so it can evolve to a super-Hubble scale for quite a long time, and eventually will after the inflation, this super-Hubble scale mode will re-enter the Hubble radius mode by mode. So, and that is the causal mechanism to explain the formation of the larger scale structure. But regarding the bounce cosmology, the diagram is quite different. And one can imagine when universe was contracting, it already starts from a very low n scale and a very, very empty, very, very large scale. So at that time, the universe approached to the Minkowski background, and one can imagine regarding the Minkowski space-time, all of the fluctuations are automatically originated from the quantum mechanism. It could come from the quantum mechanical fluctuations, or, for example, some thermal fluctuations. And along with the universe is contracting, the co-moving Hubble the co-moving Hubble radius is shrinking as well. So you don't really need to change the physical wavelength too much, but all of these perturbation modes can automatically exit the Hubble scale during the contraction. And after the bounce, when the universe begin the thermal expanding phase, then all these modes can once again re-enter the Hubble radius mode by mode. And that part of the story is pretty much similar to what has happened for inflation cosmology. So then these two, although the diagram is different, but there are so many similarities between these two scenarios. So the question is, what about the prediction of the bounce or post-prediction of the bounce? And can it be as successful as inflation? So then we go back to more details of the perturbation theory within the bouncing background. Yes, please.
Yes, you have essentially 3 minutes to go. Yeah.
2 minutes.
Yeah, 3 or 4 minutes. You can go ahead.
Okay, sorry. So then let me just go quickly. Okay, so I'm not going to the details of this perturbation development, but just mention a little bit what we have achieved. That is, if we consider a matter contracting phase, then we are able to get the scale invariant path spectrum. This is a good example to illustrate the existence of the alternative scenarios. And well, I'm not going to much details of this. Oh my gosh. So the point is, I want to mention, even this scenario is successful, we still have the more instabilities. Let's say if we look at the evolution of the sound speed square, and this value around the bounce point can be negative. So that means for the non-singular bounce realized by Hondesky Lagrangian, the curvature perturbation still could become unstable in the UV regime due to this existence of this negative sound speed square. And later on, people check through the whole potential pathologies, including the ghost gradients instability and even also include the superluminality constraints. So this is a very overall check of regarding the perturbation theory based on the bounce. And just here, I want to mention, along with the idea inspired of the gradient instability, we realize there's a theoretical no-go that constrains the construction of non-scalar bounds within the Horn-Density theory and some beyond the scenarios. And later on, there are some very good idea that is to develop the effective field theory description, and that shows that some operators, if we can introduce, then these operators can cure the gradient instability. Typically, we consider the delta k times delta g00 and the Ricci scalar of the 3 dimension times delta g00. And well, I think that is eventually what I want to carry out is very recently we found a very consistent way to include these operators is the so-called DHOST theory. It is this theory can allow for the higher order Euclidean Lagrangian equation, and but is required to contain only one propagating scalar degree freedom. So the Lagrangian is write down as the following, which is quite complicated, but we just take some examples of the DHOST theory that shows the sound speed square evolving through the whole background evolution to be well, first one is not, if you go back to the negative one, but the other 3 cases is corresponds to the examples that we include the DHOST operators, and that DHOST operators exactly evolved the effective field theory operator. So then that can overcome the negative sound speed square issue. However, in general, for all these examples, the value of the sound speed square seems to be evolved to larger than unity. So that means this kind of a model has the potential danger of the superluminality issue. So, and this is still an open question that we still don't know how to overcome. And we also take some more examples here. I'm going to skip the observational constraint here and just give you just to give you the summary of what I want to share today. So what I just want to mention is the non-scalar bounce cosmology indeed has a very promising advantage that is to avoid the Big Bang singularity. And if we want to get a scale invariant path spectrum, a typical way or very relatively successful way is to introduce a phase over matter contraction. And a single field model of non-singular bounce can be achieved. And if one can realize the combine the matter contraction and the Ekpyrotic contraction, then this cosmology is classically stable against the anisotropy as well as free from the ghost instability. However, it was found the single field model of the if it is of a Horn-Density type, then it still suffers from the very short period of the gradient instability during the bounce due to the theoretical no-go. And then it inspired the more attempts in the theoretical construction, namely the DHOST construction. And I didn't mention, but I do want to carry out is for single field model of non-singular bounce, it typically fails to meet with the current observational constraints because of the tension between the non-Gaussianity and the tensor to scalar ratio constraints. Overall, I want to say, in order to obtain a healthy version of non-singular bounce cosmology, one should keep in mind the above theoretical and observational challenges. So that's all I want to share today. Thank you very much.
Okay, so thank you, Professor Kai, for this nice talk. We have quite a few, 2 questions. Maybe we can just ask these questions right here and then finish this discussion. if anybody has any other questions, maybe they can write in the chat box, and later on we can discuss. So maybe we can just take two questions. Rathul Nath, if you can unmute your microphone, then you can just ask.
Okay. So I already saw some questions in the chatting room. So Rathul mentioned.
Yes. Can you hear me?
Yes. I
Yes.
can hear you very clearly.
I just have a question. You have mentioned that in your model, gauge condensate model, the anisotropy is still negligible during the bounce. But maybe did you mention about the spatial curvature, whether it is small or can be negligible? Or?
In fact, the spatial curvature can be included when you deriving the background evolution, but that doesn't really affect if you make use of the gauge condensate to drive the bounce. So basically, the spatial curvature, if you have listened to the talk by Professor Patrick Peter, he must have told you a positive spatial curvature indeed can also yield a bounce because it effectively contribute a negative any density, right? So while regardless of the positivity or negativity of this contribution, when the universe was contracting, and if you have some other field components or matter components to coexist, then the effective equation of state parameter for the spatial curvature actually equals to -1/3. And that means along with the contraction, this term has already become secondary if the contracting phase is long enough. So then when the universe reaches the bouncing phase, so this contribution has already become quite negligible unless you have some very delicate construction so that you can reserve the contribution of the spatial curvature around the bounce.
Will it affect the perturbations at the perturbation level?
Yeah, the perturbation level is this is actually a very good question. Previously I mentioned at the background level, yeah, it's okay. But if you write down the perturbation equations, then I believe the spatial curvature actually has some kind of the infinite. I remember it can yield some kind of the infinite cutoff for the primordial perturbations to be imprinted in the, for example, the same observational window. So that means if you develop the perturbation theory, then this curvature indeed can put some impact on the perturbations.
Okay, thank you.
Right.
Okay, so maybe I think Sriram has some question. Maybe we can keep it for the later discussion. So
okay, yeah, sure.
So with this, let us thank Professor Kai again, and I also request Professor Kai to be online for this whole session.
Sure.
So that later on, if anybody has any question, that we can discuss. Okay, thank you, Professor Kai.